Okay, in this lecture, we're going to talk about going faster than n squared, and we're going to break this part of the lecture of going faster than n squared up into multiple parts. This is just part one, and it'll be pretty quick today, or in this lecture. And as a review, we saw in the last lecture that comparison-based sorts that only compare and swap adjacent items in the array have a speed limit of big omega of n squared, such as bubble sort and insertion sort have this property. And we said if we want to go faster, we conjectured that we might have to compare and swap things that are further apart in the original sorted array. So let's talk about heap sort. Okay, heap sort is our first such faster algorithm. Heap sort is very simple. The first step is to insert, there are two steps. The first step is insert everything into a heap, perhaps a min heap. And then the second step is to remove everything from that min heap. And of course, if it's coming out of the min heap, it'll come out least, and then second least, and then third least. It'll come out in sorted order, and we can just place it back in the array. If we do this, what's the running time of this operation? Well, inserting into a min heap takes log n time for one item, but we know that if we have an entire array, we can turn that array into a heap using the make heap or build heap algorithm in order n time. Okay, that runs in order n time, and as you recall, it starts from the second lowest level of the heap and goes from right to left and bubbles down each of those, and then goes up one level and then bubbles down each of those right to left. And it's a very simple, the make heap algorithm is very simple if you've already implemented bubble down. Removing every item, which is removing the root over and over again, costs log n each remove. And so this is going to be order n log n because we have to remove that many items. Removing n items, and each one costs log n time. So the analysis for this, let's go back to our sorting analysis table. You recall that we had these analyses of bubble sort, insertion, and selection sort. Let's now add heap sort. The big O, okay, is n log n, as we see down here, right? Of these two operations that we have to do, the slowest is n log n, okay? Now what about the big omega? Well, this is also n log n. Why is it not n? Well, because we still have to put everything into the heap, and then we still have to remove everything from the heap, and that removing everything from the heap costs n log n. Is this a stable sorting algorithm? Well, no, it's not, because if you have two items that have equal value, it may be that that they come out in a different order, just depending on the tiebreakers that you have in your heap. Can it be done in place? Well, I'm going to defer this question, and we're going to come back down here. Can we implement heap sort in place without using an additional, we have the original array that we want to sort, and it seems like we have to have this additional data structure for the heap. It turns out that we can use the original array and only the original array and sort the entire thing in place. But in order to do that, what we need to do is we need to use a max heap instead of a min heap. And this might seem odd at first, but here's the reasoning. If we build a max heap out of our array, the first thing that we remove from the heap, the root of the heap, will be the largest item. Where do we want to put the largest item? We want to put it at the back of the array. Well, every time we remove something from a heap-based array, guess what happens? We get an empty slot at the very end of the array, the place where we want to put that thing. So let me give you just a quick visualization of what is going on here. If we have, here's a visualization of a heap, okay? This is just our visualization. This is not reality. The reality is, after we've built our heap, after we've taken an array and we've run the make heap or build heap algorithm on it, we're going to have an array that looks like this, okay? The values are 10, 7, 9, 3, 5, 1, 5, and again, that's 10, 7, 9, 3, 5, 1, 5 in level order. If we were to remove something from this heap, what do? Well, we're going to take this item, 5, and move it up to the root because it's the last item in this array, and it's the last item in our heap. So if we move that 5 up to the root, and I'm not going to illustrate it here, but if we take this 5 and we essentially remove it, and we then put it at the top, right, and then bubble it down, guess what we just did? We just created a hole in this array right here, and what should go in that hole? Well, the 10 that we just removed. So the point here is that if we use a max heap, we can do heap sort in place on the original array itself, because every time we remove something, we're removing the largest item that will need to go towards the end of the array, but we just created an empty spot at the end of the array. So we would go ahead and bubble down 5. It'll go somewhere. The next time we remove, we would end up probably moving this 1 up to the root again, and then we would have an empty slot right here for the next largest item, which of course would have been the 9. Okay, the 9 would have come up here. Well, I guess we could just bubble down 5. If we bubble down 5, let's continue this example. We would swap 5 and 9, and then the child of that would be just this 1, and that would be, we would be done with our bubble down. So if we wanted to remove one more item, again, we would swap the 1 and the 9, and guess what? The 9 is in the appropriate place, and so is the 10. So we can do heap sort on an array in place. So the answer to our query of can we do it in place, the answer is yes. Okay, so here's our first faster algorithm, faster in terms of big O. It's n log n. Let's look quickly then at another algorithm, an algorithm I sort of just made up, but it illustrates some of the properties that we're talking about. What I'm calling tree sort. Tree sort, as I say, it's not really a thing. You won't actually see this algorithm in practice, but you could build this. It's quite simple. Let's insert every item that we want to sort into a balanced search tree, a balanced, say, binary search tree like an AVL tree, and then we can traverse the tree in order. And when we traverse the tree, we would put all the items back into the array that we want to put these sorted items in. Okay. What's the cost of this? Well, inserting an item into a balanced binary search tree costs log n per insertion. So we have n log n for all of the n insertions. And then traversing the search tree, we can do that in order n time if we're careful about our code. So the overall running time for this algorithm is n log n. Now I do want to call your attention to sort of a duality here between heap sort and tree sort. Heap sort, the slowest part is removing everything from the heap. It's very quick to get it into a heap order. With tree sort, since we're putting into a more strict order, that's the thing that costs us more time, and just getting things out of the tree in order is the cheap thing. So we have this duality of heap sort is fast at putting it into heap order, but slow at getting everything out of the heap. Tree sort is slower at putting things into the tree and faster at essentially traversing the tree to find out what order they ended up in. Okay, so tree sort is going to be n log n in the worst case. What about in the best case? Well, it's still going to be n log n. Okay. Is it a stable sorting algorithm? Actually, yes. It could be easily made stable, because if you have two equal items, you could append them in the order that you see them as you go through this array. So in other words, if this is a node that represents the value 5, I could then, if I see another 5 later in the array, I could append it in a list to this same node, and I could append them in the order that I see them. So this is actually a stable sorting algorithm. Can it be done in place? Well, no, not really. We need this extra tree data structure in order to keep the items that we're trying to sort. Okay, so that's heap sort and tree sort, and they're very heap sort is in fact a very widely used algorithm in practice. Tree sort I just made up, but it's also could be useful. And we'll talk in the future about merge sort and quick sort in later lectures. So come back for those.